Let's take a look at an example that's going to require integration by partial fractions. First of all, this integral on the screen is a good example of one that screams immediately for some substitution before we even get to some other integral technique. There's e to the x's all over the place. Maybe we can tidy things up. For example, if I make the substitution u equals e to the x, du needs to be e to the x dx. And hey, look, I've got that up in the numerator. This e to the 2x happens to be e to the x squared, right? And so I can reconstruct this integral with my substitution. Here's a u squared minus u, and then e to the x dx is all du. There, that looks a little bit better. And then we look at that denominator and we say, oh my goodness, that looks like some factoring could come into play. So, common term of u. There we go. Now, that is as far as I can go with manipulations up front just to try to simplify the integrand. Now I'm stuck, because I don't have any integral formulas for this particular structure, at least in terms of what we've seen so far. So for the moment, I'm going to really emphasize what that integrand looks like by pushing the du over to the side a little bit. We're finding the antiderivative of this fraction 1 over u times u minus 1. Let's take that 1 over u times u minus 1 off to the side by itself for a second. This looks an awful lot like somebody has gone and found a common denominator and mushed together a couple of terms. We are going to discover what those original terms would have looked like. And so we'll have like a before and an after. The thing we're looking at now is the after in terms of the finding of a common denominator. We're going to go in a time machine and send it back to its before, because its before probably looked like this. So can you imagine that this denominator right here was created by finding a common denominator between a couple of separated terms like this? And if we wanted the antiderivative of this, well, we don't know how to do it, but if we then exchange that for the antiderivative of this, now we're just looking at a couple of natural log terms. And so what we have to do is find out what are the mystery numerators that make these two things equal. Assuming that these particular structures, these ratios, are as simplified as they could get, in other words, any cancellation that could happen has already happened. If the denominator is u to the first, then the worst case scenario is that above is a constant. And then same thing here. If there was a term with a u up here, and there's also a u down here, that means there's still more simplification to be done. And we're going to assume that we've gotten the base case. So how does this work out? What are the values of a and b? Well, let's do a little manipulation. I'm going to multiply both sides of this equation by that full denominator, because this looks gross the way it is. So I'm going to multiply both sides by u and by u minus 1. That'll turn the left-hand side into a 1. Over here, if I multiply this term by that entire denominator, the u's are going to cancel. And when I multiply this term by that entire denominator, the u minus 1's are going to cancel. Now, technically speaking, when we're looking at this version of that fraction, u equals 0 and u equals 1 are not in the domain of that function. Or in the domain of this function, meaning also we're not supposed to be looking at u equals 0 and u equals 1 there. However, those values are going to be helpful in terms of discovering what values of a and b would make all this work out. This relationship has to work no matter what u is, which means this relationship has to work no matter what u is. Up here, we're not supposed to use u equals 1 or u equals 0, and so technically here we shouldn't be looking at them either, but I'm going to cheat. I'm going to say, what if u happens to be 0? This term goes away. If u is 0, I get 1 equals a times 0 minus 1, or 1 equals negative a, so a is negative 1. Ta-da! And if u equals 1, I'm going to get 1 equals, if u is equal to 1, this whole term vanishes, and b times 1. And so immediately I've discovered the values of a and b that will make this algebraic structure work out. I'm cheating a little bit with the use of u equals 0 and u equals 1, but shh, just like in the last section, don't tell anyone. We're all friends here. So what that means is that this 1 over u times u minus 1 is actually equal to negative 1 over u plus 1 over u minus 1. And you could do this reconstruction just to check it if you wanted to. Start with these two things, find a common denominator, put everything together. You'll end up with this. What that means is that the integral of 1 over u times u minus 1 du is the integral of negative 1 over u plus 1 over u minus 1 du. Can't do it? Haha, can do it. This is negative natural log of u. This is natural log of u minus 1. And we have a big plus c. And then, don't stop, because remember, the original integral was not presented in terms of u, it was presented in terms of e to the x. And so let's put it all back together again. This means that the original is going to end up being negative natural log of e to the x, and I don't need the absolute value bars because e to the x is always positive, plus natural log of e to the x minus 1 plus c. And if you really wanted to be slick, you could use properties of natural logs to combine these two things into a single natural log of a quotient. I'll let you decide if it's worthwhile. But this is the heart of integration by partial fractions. You're integrating what is a rational function, and you can say, yuck, well, I don't want to integrate it like this. In fact, I can't. Let's make a little time machine and see if we can take the rational expression that we have and break it down into its individual pieces, or its parts, or its partial fractions that would themselves be easier to integrate on a one-by-one basis. And then discover what constants make that work out with a little bit of algebra, and then reconstruct the integral, get her done. You'll have to visit a lot more examples to see other ways you can do the figuring of these constants. There's a heck of a lot of subtleties in problems like this, but this is a starter example, and I think it's a good one.